So question 10 from the same problem set. Okay, so I've answered the first bit of this question. So Q10 problem set 3. I've answered the first bit, and the second bit is the investigation part, which we can maybe do together. So the question is, we have A, B, C, D, and E are real. I'll just write that, are real. And yeah, so the fact that they're real means there's so much to check. Like we're not just restricted to the integers or anything, which might make it a little bit daunting, but still I think the integers are a good place to start because we know how to square integers. Oh, right, and the question is, so we've got these 5 values that are real and they're linked to each other. They have relationships to each other via these 2 equalities. So E is equal to 40 minus A plus B plus C plus D. And E squared is equal to 400. Equal to 400 minus A squared plus B squared plus C squared plus D squared. Okay. Sorry, just give me 1 second to get myself set up properly. Okay. Okay, back to the question. So, yeah, so we've got 5 real values, A, B, C, D, and E. And what we know about them is that these 2 equalities hold. So E is 40 minus the sum of the numbers, and E squared is 400 minus the squared sum, or the sum of the squared numbers. And the question is, find the maximum value of E such that this is possible. So let's just gain some understanding of what our range is exactly by having a think about what's possible and what's not possible. Because just by looking at it, you might not exactly feel like it's obvious that there is a range that we're going to stick to. But I think this equation here gives us a good starting point to determine a range. And that's because A squared, B squared, C squared, and D squared, we know to have to be greater than 0. Because numbers squared are always bigger than 0. Or bigger than or equal to 0, sorry. Because they're allowed to be 0. Okay, so that immediately gives us the fact that e squared is less than or equal to 400. Okay, so what would happen if e was equal to 400? E squared was equal to 400. Then that would mean that A, B, C, and D would have to be 0 to make that happen, because 400 minus 0 is 400, which means that E is equal to 40 minus 0 from the first equation here. But then 40 squared is 1600, which is not 400. And E squared is supposed to be 400. So that means that E cannot equal 40. Or E cannot equal the square root of 400, because that's the case we were starting with. So that means E is less than 20, which is the square root of 400. Okay, so we've got E less than 20. So in fact, we have that A, B, C, and D are greater than 0 and definitely not equal to 0, because we just investigated that case. And we have that E squared is not equal to 400 because we just investigated that, and it's not possible. Okay, so cool. So that means we've already established that E is strictly less than 20. Okay, and I think another thing to do to establish a range for E. So to establish a range for E, I really just mean let's narrow down the real number line to see where we're trying to concentrate our efforts, basically. So another good way to do this is we've got an upper bound. And that's good because if we're looking for a maximum value, we now know that we can't keep pumping up E to be as big as we like, because we've got this maximum capping value of 20 already. So the good thing about questions that look for maximums or minimums is that for a lower bound, you just look for values of E that work. Because if there's a value of E that works, meaning that there's a value of E such that these equations make sense, and there are corresponding values of A, B, C, and D that make these equations true, then that value of E is a lower bound, because it's possibly the maximum, but not necessarily. So basically, if there is an E that works, we know that the maximum can't be smaller than that value of E, because we already know that that value of E works. Okay, so for a lower bound, look for values of E that work. So let's start with a nice, potentially easy one. And E equals 0 happens to be quite nice. So if E equals 0, then that means that E is equal to 40 minus A plus B plus C plus D. So this has to equal 40 for E to be 0. And in addition, E is 400, E squared is 400 minus A squared plus B squared plus C squared plus D squared. And since E squared is 0 squared, which is 0, then I know that this has to equal 400. And the values of A, B, C, and D that give us this are 10, 10, 10, and 10. So 10 plus 10 plus 10 plus 10 is 40. And 10 squared is 100, plus together 4 times, we get 400. Okay, so that means immediately that E is greater than or equal to 0. So we've already narrowed our range down from the entire number line to values between 0 and 20. Okay, let's keep going. So what's another nice one? E equaling to 10 happens to be nice because it's kind of similar to the E equals 0 case. So if that's true, then E equals 40 minus A plus B plus C plus D. This has to equal 30. And E squared is 100. So that means E squared equals 400, 400 minus A squared plus B squared plus C squared plus D squared. Then all of these have to equal 300 to leave behind the 100. And you can see it's kind of similar to the case before. We just make 3 of them equal to 10 and the other one equal to 0. So A, B, C, and D equals these values works. So now we've narrowed our range down even more. We have that E is greater than or equal to 10. So that's interesting. Let's see if we can narrow it down even more. So I know that I've just focused on integer values, but the reason for that is because it's a good place to start since we're all a lot more familiar with doing calculations with integers than we are with non-integer numbers, because I can square them and subtract them easily on paper. And so that's why we're just thinking about integers. Okay. So at this point, you might want to, at this point, you might be tempted to look at E equals 19, just because you know that E is less than 20, and you want to make E as big as possible. And we know how to do calculations with integers. So you might be tempted to try E equals 19. And so let's have a go at that. And let's try and find A, B, C, and D, which works. So if E is equal to 19, then E squared is equal to 10 plus 9 squared, which is 100 plus 81, plus 2 times 90, which is 180. So that's 280 plus 81, which is 361. Okay. So that means we've got E equals 40 minus A plus B plus C plus D. Well, if E is to be 19, then we need this to be 21. And E squared is 400 minus A squared plus B squared plus C squared plus D squared. Oh, sorry, I should have put brackets around these the whole time. Sorry. I'm going to do that now so that no one's confused. Which means that all of this has to equal the difference between 400 and 361, which is 39. Okay. So what can we do? Okay, so let's just write these out just to know what we're working with here. So we've got that A plus B plus C plus D has to be 21. and the sum of the squares has to be 39. We want to see if we can find values of A, B, and C, and D that give this to us. So is that possible? And just for a bit of intuitive understanding, like it's possible that like, let's say, in order to get 21, then the magnitudes get so large that this thing fails to happen or something. But maybe it'll be more intuitively clear why it can't work if we can find a contradiction. So let's just think about what's happening here and try and do some sizing stuff. So from this one here, I think, once again, because we know that all these values are positive, it's a good place to start with trying to establish some upper bounds or lower bounds or whatever. So it's a good place to start because these are all positive. None of them can be negative. And that immediately makes these have to be not too big, because if they were too big, we would surpass 39. So what do I mean? I mean that A squared, B squared, C squared, D squared, not too big. And what's an example of too big? So an example of too big is if one of them was equal to 7. If any one of them was equal to 7, then A squared would equal to 49, which means that A squared plus B squared plus C squared plus D squared would have to be bigger than or equal to 49. But that's greater than 39. So that's not possible. So that means that what we've discovered is A, B, C, and D all have to be less than 7. Otherwise, it would be too big and we can't get that second equation. So that's a good upper bound. Now let's focus our attention to the first equation here. 21. So I've got 4 numbers. I've got 4 numbers that I want to add together to give me a value of 21. So if 21 is the length of this interval, I'm basically trying to chop it up into 4 components such that they add together to give 21. So if this is the length of A, this is the length of B, this is C, this is D. So it's clear that if we make one of the components smaller, then the rest have to expand to cover that in order to make the sum still equal to 21. So just based off that idea, let's see what the most regular case is. So the most regular case would be if A equals B equals C equals D. And if that was the case, then each of these would have to be equal to 21 on 4 because there's 4 of these numbers added up to give 21. This is, well, 21 on 4 is greater than 5, isn't it? So in the regular case, they're all greater than 5. Now, if we start to make one of these bigger, then some combination of the other ones will have to become smaller to account for that. Or if we start to make one of them smaller, then the other ones have to get bigger. So just based on this idea of balancing it out, then we can comfortably say that at least one of A, B, C, and D has to be bigger than 5. If all of them add up to 21, then there's going to be one that's big enough. Because if they were all less than 21 on 4, then they wouldn't possibly add up to 21. So that means that we've got at least one of them bigger than 5 and also less than 7. So let's start to work on these conditions. I'm going to start with this less than 7 thing. Oh, actually, I'm going to combine the two. So combining the two, we have at least one of the A, B, C, or D is greater than 5 and less than 7. Okay, I'm just gonna fence this off, fence it off so that we don't get confused. Okay, that's good enough. All right. So at least one of them has to be bigger than 5 and less than 7. So let's just pretend that the one that I'm talking about is A. Doesn't matter which one I choose. It's we'll log A. So we'll log 5 less than A less than 7. So if that's the case, then I've got B plus C plus D, because originally I had that the sum was equal to 21, right? So if it's less than 7 and bigger than 5, less than 7 means that the other 3 have to be at least 21 minus 7, which is 14. Let's do a similar thing for the squares now. So I can use the other part of the inequality. I've already used the bigger part. So what about the greater than 5? I'm going to use that on my other equation, which said that the sum of all the squares had to be 39. So that means that this, if a squared is bigger than 5 squared, which is 21, what 25, what am I talking about? Then b squared plus c squared plus d squared has to be less than 39 minus 25, which is 14. Okay, so I think you can probably immediately see that this is unlikely to work out because these have to sort of be small enough to get 14 as the sum of squares, and yet they're supposed to add up to 14. So just by looking at it, you're probably convinced that it's not going to work out, like that's not going to be possible. But again, to make that really clear and rigorous, we can do this Yeah, okay, we can do this thing again where at least one of them has to be big enough, right? Because if the whole thing needs to be greater than or equal to, sorry, greater than 14, then at least one of them has to be big enough. So in particular, one of them has to be at least 14 on 3, because there's 3 values here. So if they were all smaller than 14 on 3, then when you add 3 of those together, you'll get something that's smaller than 14. So one of them is bigger than 14 on 3. And what is this? That's like 4 2/3. But then 4 squared is already equal to 16, which is bigger than 14. So it's not possible that when you square everything and add it up, you'll get something smaller than 14. So that's not smaller than 14. And that leads to a contradiction. So that's the symbol I like to use for contradiction. Okay, so that can't work. We found that if e is equal to 19, then all this stuff happens. So if E is 19, then we get these conditions on the rest of the numbers. And we basically saw that we have some bounds for each of the values. So at least one of them is between 5 and 7, which basically makes the rest of the stuff impossible just by doing all this sizing stuff. Okay, so that does not work. So, okay, 19 doesn't work. Yeah, unfortunately, we can't really say that E is less than 19, because what if there was a value between 19 and 20 that worked? So we can't say that. That was more just to get a feel for the question, I guess. So let's try some more values. And so I guess the 19 it didn't really get us anywhere, but we understood that it couldn't work, which was valuable in itself. But let's try some other values of E. So what do we have so far? I think so far our lower bound is 10, because we saw that 10 works. So what about E equals 15? Let's try and crank it up a bit, because if E equals 15 works, then that will be our new lower bound, which will make our range even smaller, and we can check less stuff. So does E equals 15 work? If E equals 19 worked, that would have been in lower bound, but unfortunately it doesn't. So can 15 be our lower bound on our answer? Let's see. So E equals 15 means that E squared is equal to 225. And that means A plus B plus C plus D has to be equal to 40 minus 15. Just from that first equation, which is 25. And A squared plus B squared plus C squared plus D squared is equal to 225. So 400 minus 225, which is 175. And it turns out that 10, 5, 5, and 5 works, because if these three are all 5s, then this is 25 plus 25 plus 25, which gives 75, and this is 100. So 175 is what comes out of that, and obviously 10 plus 5 plus 5 plus 5 is 25. Okay, so that means that E is greater than or equal to 15. So our maximum possible E is either 15 or bigger. Let's now try the next number up. So what about E equals 16? So for E equals 16, we've got 16 squared is equal to 100 plus 36 plus 120, which is 256. Okay, so we had, what did we have? We had E equals 40 minus A plus B plus C plus D. So if E is 16, then that has to equal 24. E squared was 400 minus everything all squared. And that has to then equal 144 if we're going to get 256. Okay, and what values work? Okay, well, these are all nice multiples of 12. So that's sort of a clue. let's see, does 6 work? If we do 6, 6, 6, 6, well, 6 times 4 is 24, so the sum works. And is 36 times 4 going to be 144? Well, it should, because we know that 12 by 12 anyway, okay, so 36 times 4 is 120 plus 24, which is 144. So that means 6666 actually works. So yay, we have an even tighter bound. So from this, we have, in fact, that is bigger than or equal to 16. Okay, so at this point, let's just end here and say, okay, I'm going to work with my bounds of bigger than or equal to 16 and also less than 20. Like I checked 19 and it didn't work. I could probably check 18 and 17 similarly and do some sizing stuff and figure out if it works or not, but I'm just going to cap that here. And let's try and actually figure out what the value is. And the way we're going to get a final answer is by contradiction. So we're going to use contradiction to tell us that it can't be bigger than a certain value. For an upper bound, basically. Okay. So let's rewrite the original equations. Remember the original equations were this thing here? I think it'll be useful now to play around with squares and stuff. And also recognize that all the numbers are sort of interchangeable. So if I put, oh, whoops, this was supposed to be brackets. No. Okay, so if I put everything on one side, a plus b plus c plus d plus e, I just get 40. And I also get a squared plus b squared plus c squared plus d squared plus e squared is 400. Now, this invites me to do some stuff with squares and all that. It invites me to try and square this or something along those lines. Or maybe not exactly square the whole thing. In fact, I'd say that it invites you to complete the square. So just as an example, if we did a minus 1 squared plus b minus 1 squared plus c minus 1 squared plus d minus 1 squared, what would we get? Well, we get a squared plus b squared plus c squared plus d squared from each of these expansions. But then you have to subtract 2 of their sum, because we always get minus 2a in here, minus 2b in here, and so on. But then we have to add the constant term that we add on the end. So plus 1, plus 1, plus 1, plus 1. Okay. Well, luckily I can replace stuff. So I already know what this is equal to. That's 400. I know this is 40, so that's going to be minus 80 plus 1. So that is 3, 2, 1. So I just found that this is equal to 3, 2, 1. And if I start to rename everything and call this big A, big B, big C, and big D, then it kind of goes back to the beginning, doesn't it? it's like we've got new equations that look really similar to this, but with new variables. A squared plus B squared plus C squared plus D squared equals 3, 2, 1, where A is actually small a minus 1, and so on. So then what's A plus B plus C plus D? That's just going to be equal to all of these, but minus 1. So that means I have to minus 5 from 40. So that's 35. So this sort of simplifies the problem, or at least brings us closer to something that's easy to analyze, maybe. So maybe when I say easy to analyze, I really mean that I'm trying to derive some sort of contradiction, because I've already said that we're going to get a contradiction. And you can start to see where a contradiction might arise. So just like we saw with 19 not being able to work, we saw basically that 19 couldn't work because the sum of the squares was too small, pretty much. It was too small for this to be able to occur. And that's how we got a contradiction for 19. So we're going to exploit a similar idea, and we want this to be too small in order to get a contradiction. So if we want this to be too small and get a contradiction, then we might want to try and make it equal to 0. So try to get a squared plus b squared plus c squared plus d squared equal to 0 or something like that. So that, and then see what the sum is. So if that's going to happen, then let's see how we might get 0. So looking back over here, in general, if I'm going to do a minus k for some value of k squared plus b minus k squared plus c minus k squared plus d minus k squared, then what's going to happen? So that's going to have to be what's going to happen? We're going to get all of them squared. And then we're going to have to subtract 2 times k times the sum. And then we're going to have to add up 4 values, 4 multiples of k squared, or 4 lots. And then that's 400, as we can see, minus 2 times 40 times k, which is 80k, plus 4k squared. So So let's just try and get a smaller number to begin with. Maybe not make it equal to 0. So let's try 8. A minus 8 squared plus B minus 8 squared plus C minus 8 squared plus D minus 8 squared. So that's going to be equal to, I've just done the formula, 400 minus 80 times 8 plus 4 times 64. So 400 minus 640 plus 16 plus 240. Okay. And what does that give me? Well, minus 240. Oh, so it's just 16. Cool. Wait, is that right? Okay, so basically this tells me if A is equal to A minus 8 and so on, we've got A squared plus B squared plus C squared plus D squared. Oh, I've forgotten all my E's, haven't I? Plus E squared. Whoops. Whoops. Plus E squared. Then we've got this is equal to 16. And what else do we have? A plus B plus C plus D plus E is just 40 minus 8 times 5. 5 lots of 8. 40 minus 4, 8 times 5, which is 0. Okay, so they have to add up to 0, but give me 16 when we square them. So clearly some of these values are going to be negative in order to make the sum equal to 0. Well, I think at this point we can start to use our bounds. So at this point we've already established that E is greater than or equal to 16 and E is less than 20. So how about we try values of E bigger than 16? So what we do is suppose that E is bigger than 16. Then big E, which is little e minus 8, is 8. Oops, bigger than 8 because E is bigger than 16. Cool. So what is E squared? E squared is 64. But that's not possible. Okay, so that's not possible because we already saw this. We already saw that when we sum everything up, we only get 16. So we successfully got our problem to small enough numbers such that we could derive a contradiction. So that means that E cannot be bigger than 8. Wait, something feels a bit wrong. What have I done? So something feels wrong because E should be equal to 8, because we already saw that E equals 8 works. So I shouldn't get a contradiction just yet. What has happened? So I think this thing here might have been wrong. Oh, 5 now, right? Should be a 5 because I forgot about my E's. And then that has the effect of doing this, which gives me a 320. So what's 320 minus 240? 320 minus 240 is 80. Okay, so that's what's happening. There we go. That's better. Okay. So we're not quite done. We haven't derived our contradiction yet. Okay, but this is still true because I did the 5 properly. Okay, so we've got the squared values add to 80 and the original values add to 0. And so we're trying to suppose that E is bigger than 16, which means big E is bigger than 8. So big E squared is bigger than 64. And so we can continue by looking at what that means for this equation. So that means A squared plus B squared plus C squared plus D squared is less than 16. And what does it mean for this equation? If E is bigger than 8, then that means that A plus B plus C plus D is smaller than -8 to balance that out. Okay. Okay. So I think we can derive a contradiction from noticing that this and this have a ratio of 2. So 16 is equal to 2 times 8. So I think I can get a 0 if I do something interesting. So if I add 1 lot of the first equation to 2 lots of the second equation, then I can get a 0. And what is the effect of adding 1 lot of this to 2 lots of this? It's going to look almost like I'm completing a square. So, okay, but it might not work because I'm going to have to add the constant term back, but let's just fidget around, right? So if I do a squared plus b squared plus c squared plus d squared plus 2 of a plus b plus c plus d, then to complete the square, I would have to add 1 and get a 4 here. And this would just be equal to a minus 1 squared plus. Okay, so that's not quite good enough because this doesn't give me a contradiction just yet, but I can actually bring this down even further. So if I did 16 plus some value times negative 8, some value k, 2k, plus k squared 4 times, then I want to get 0. And the value of k, which gives me that, is, well, what's that? 4k squared minus 16k plus 16 equals 0. So k squared minus 4k plus 4. And so that means that k equals 2 could work. And so let's try k equals 2. Let's try and do a minus 2 squared plus b minus 2 squared plus c minus 2 squared plus d minus 2 squared. So this is going to be equal to, well, not equal, but if I want to use my equations 1 and 2, what happens is, okay, no, let's do the equality first. So we've got all of my first terms squared, and then the cross terms are going to give me the minus 2 times a plus b plus c plus d. And then the plus 2 squareds are going to give me 4 lots of 2 squared. And now I can start to use my equalities, my equations 1 and 2. Well, they're not exactly equations, they're inequalities. And so that's less than, well, a squared plus b squared plus c squared plus c squared, d squared is less than 16. Now, ooh. Oh, I plussed, didn't I? Okay, since I added up here, I did plus 2k. Then then what I was actually looking for was, so this was actually equal to the sum of a plus k squared from a to d, because this was all the terms squared. This is all the terms. Yes, so if I did a plus, then I really meant this instead of a minus k. So I actually meant this. Okay, good, good. Now I can start to use my inequalities. So plus 2 times a plus b plus d, c plus d, which is negative 8, plus 16. No, not plus 2. It's my plus 4. So the plus 4 comes from my cross terms. My cross terms would be plus 2 times 2a, which is plus 4a. Okay, and now that is equal, finally, to 16 minus 32 plus 16, which is 0. Okay, so altogether what I've got is this sum of squared terms has to be less than 0. And that is obviously not possible with real numbers. And we got the less than 0 from supposing at the very beginning that e was bigger than 16. So if e is bigger than 16, then for some real a, b, c, and d, where a was equal to a minus 8, and so on, those are all real, but this all squared and added together needs to give us something negative, and that's not possible in the real number world. So that means we've derived a contradiction. So altogether, we've got e is bigger than or equal to 16, and e cannot be greater than 16. And together we get that e is equal to 16 is the maximum value of e.